Hi everyone, Big Mac here. Welcome back to, I guess the first part of my solutions to my, favorite calculus questions video. So if you guys haven't seen that video yet, I'll put the links here. That's why I left plenty of white space. I'll be giving you guys plenty of annotations and other stuff. This will be just the first video of solutions. I am only going to be covering the first two questions that I asked in the first video. So let's go ahead and get started. I'll quickly review the question as well. So exam 1, we just had our pre-calculus review. I asked how many solutions are there to the following equation, 2 equals 3 plus 2 cosine of 50x, on the interval of x being between 0 and 4 pi. I did have one typo, which I will admit I had for the video, not for the actual test itself. For the video I said that choice D was actually 100. In fact, it should have been 200. So hopefully if you guys actually tried working out these problems yourself, you guys would have been able to answer that correctly, knowing the fact that choice D was actually 200. All the other options are still the same. Again, ideally, you could use your calculator, but it shouldn't take you more than 3 minutes to solve this particular problem. So of course, the typical approach that students did was they tried to solve it in different ways, but it was very ineffective. Of my students who guessed on that question, I don't know if they guessed or if they thought they knew the answer, but only about 10% of my students actually got the question right. If given a 5-choice multiple question problem, that's worse than pretty much picking at random. You would hope at least 20% of the class gets it right. The most common answers were B and E. So quickly going back over here, we have the B is 12 solutions and choice E being none of the above. So what happened? Why did they choose these answers instead of the correct answer? Well, let's try and look at what's going on in this actual question. So, solving with the original equation, 2 equals 3 plus 2 cosine of 50x, we can simplify this thing a little bit, and we narrow that down to solving the equation cosine of 50x is equal to negative 1/2. So then, of course, 50x has to be the inverse cosine of negative 1/2. If we're looking at solutions in between 0 and 2 pi, then we in fact know that the inverse cosine of minus 1/2 would be at 2 pi over 3 as well as 4 pi over 3. Again, some people use negative pi to pi as their solution range. Some people go from 0 to 2 pi. Since we were focusing on only positive solutions in the set, I decided to use the 0 to 2 pi typical range of solutions. So of course we have 2 pi over 3 plus 2 pi times different multiples, where k is the some time of integer. We can keep going and around and around the unit circle. Likewise, at 4 pi over 3 plus 2 pi plus 4 pi plus 6 pi, etc. But of course this is equal to 50x. So to solve for x by itself, we have to divide everything through by 50. So we do in fact simplify these answers, and we get a definite range of numbers here. Let's see if my mouse can pop back up here. There we go. So on average, each solution is separated by pi over 25. So thinking about that in terms of decimals, that's not a whole lot. That's maybe an eighth, more or less. And we're trying to figure out what these solutions are on the range of 0 to 4 pi. 0 to 12.5-ish, 5.6, something like that. But so the important thing was not what the solutions are. The important thing for this question was how many are there. I didn't actually care whether or not a student was able to actually find the solutions. I just wanted to know how many were there going to be. Of course, the important thing here is that for each period, we're going to have 2 solutions. The other important part of this equation was that fact that we had a wave number. Some people call it a wave coefficient, but basically that coefficient inside of our cosine or sine function, that our wave number was 50. So again, we use that number in a lot of different ways. We can use it to try and find the period of a function, and that number also tells us how many periods our function has in between a standard 0 to 2 pi breadth. So if there are 50 periods of this function between 0 and 2 pi, then between 0 and 4 pi, we're obviously going to have 100 of these periods. So like we just saw on the last slide, we saw that there are going to be 2 solutions per period times 100 period gives us 200 solutions, D being the final answer. But that's not what students' calculators said. On a TI-83, I'll show a video of this right now. If students tried to graph the function cosine of 50x, or what was it, 2 or 3 plus 2 cosine of 50x, when they graphed the window, it looked like there were 12 solutions. 12 was one of the choices on the exam. Likewise, on students that had a TI-89 calculator with the same window, that resulting function looks like it has about 40 solutions. I don't remember the exact number. But what students did was they looked at the calculators. They're like, okay, I'm just going to count how many solutions there are. And hence they got the wrong answers. This is what I was talking about. Oops. Click.
Now the photographic proof of what I was talking about. Suppose we wanted to graph cosine of 50x. Our window being from 0 to 4 pi and our y just being from -1 to 1. Well, when you look at the graph of this thing, it looks like there were 12 zeros, or 12 solutions to the function being -1/2. So here it is in action.
So indeed, if the students used their calculator, they were going to get it wrong. Isn't that mean? So does that make it a trick question? Maybe. But the fact was, this is prerequisite material. This is things that they should have seen before, that they should understand what's going on. So really quickly, I'll just go into a brief explanation as to why the calculators are saying what they're saying. Did the calculators screw up? No. They're doing their job correctly. It just turns out that it's not fine enough. So if we were to actually look at a graph of this function, cosine of 50x equaling -1/2, pardon my MS Paint skills, but a graph would look pretty much something like this. Hopefully there we go. Hopefully I've got the mouse popping up for you guys now. But if we were to actually correctly graph this thing like it should look, we just said that there are going to be 100 periods of this function inside this little tiny window from 0 to 4 pi. It would pretty much black out the entire screen, as it were. Then I just graphed 50x equals 1/2, or cosine of 50x equals 1/2, just to get back to the basic cosine function. But even if we were to graph the original equation, it would just be as complicated, for sure. Of course, why does the calculator not do this? Well, there's a process technically known as aliasing, where obviously those data points are there, but if we space out our data points in a certain way, the resulting picture will not look like the actual original picture. So here's another situation of where the resolution basically of your data sampling is going to affect what your outcoming graph will look like. So here I've got the exact same graph of cosine of 50x. In this instance I said my delta x, so I basically measured it every pi over 12. So of course, since I'm going from 0 to 4 pi, that means I included 48 data points. However, even with this cosine of 50x function, by using those 48 data points, our graph looks like a typical cosine function that has a period of maybe a period of pi. Except, in this case we already mentioned that the period of the thing is a ridiculously small amount. To the point of pi over 25, sorry. So which is about 1/8. So the fact is, just because if we don't take our data points close enough, then unfortunately what can happen is our graph will look wrong. And so of course, if the points on the graph come out wrong, we're going to make the wrong conclusion based on what's happening there. There's a little bit more theory that goes into this thing, but basically since the calculators have a fixed resolution, so many pixels by so many pixels, when they draw their graphs, they only take so many data points. And from there, they just play connect dots for the most part. So unfortunately, if your resolution is not high enough, there is a possibility of getting the wrong graph for these things. This particular kind of thing occurred a lot more in signal processing. Definitely a issue involving electrical engineering, if you're interested in that kind of stuff. And there's a dog outside barking. Great. Quickly, let's just finish off question number 2. So we had this point 5, -3 on the graph of our original function. So our question was, which of these following points must be on the graph of this transformed function? Or instead of just having g of x, we now have g of 5x, and then that whole thing is multiplied by -2 on the outside. So we have our 5 possible points, and again, ideally, students could use their calculators, although I don't know how they would use it in this situation. But again, this is a question that should have taken a very short amount of time. This is a kind of covering material that students should have seen for sure by this time. In terms of how the students actually did, less than half of them got it right. Obviously still better than the 10% of the previous one, but their most common answer was C, 25 and -6. Why would students think of this? Well, let's try and go back to what these actual function, what this actually, the -2 g of 5x actually does for the graph of the function. So, of course, what do we know? If we know that we have this point 5 and -3 on the graph of g of x, then we know for a fact that g of 5 has to be -3. I think everybody could agree with that. Of course, what is happening to the graph when we have -2g of 5x? Well, the -2 thing is pretty intuitive. You know, if we were trying graphing this thing, the negative sign is going to flip all of our y values around. Multiplying it then by a factor of 2 is going to stretch out all of our values. I'm using my hands to explain these things, even though you're not going to be able to see this. But then lastly, that factor g of 5x, instead of just g of x, is actually going to squish in our function by a factor of 5. Going back to just our previous question with the cosine function, cosine of 50x. We took a cosine function and then we squished it in by a factor of 50, which is why there were so many periods in the last problem. So considering that our values get really squished in, we would expect our data points to be even closer to the origin in that respect, at least in the x direction. So, of course, the original y coordinate, I'm just calling it the ordinate because it's not necessarily y and x as our variables. But if we multiply this thing by -2, obviously -3 times -2 gets us to 6. Our original data point was 5, so getting that thing squished in by a factor of 5, we get 5 divided by 5 being 1. The original point has now moved to 1/6, so B was in fact the correct answer. Of course, that's in terms of the typical things that students learn in a pre-calculus course, is transforming functions, shifting them, reflecting them, those kinds of things. The fact was, this was a multiple choice exam, so I would hope that at least some of the students might have done this. Plug things in. You know, you could try plugging in -1 or 25 in for x, but the fact is we know nothing of g of -5. We know nothing of g of 125, so that eliminates 3 of the 5 choices. So, in all honesty, I was really hoping that I would get at least 75% of my students to get this question correctly. This is stuff that has been covered in previous classes. This is stuff that I mentioned during our pre-calculus review, and it was still less than 50%. Basically, people saw that 5x and said, oh, I gotta multiply x by 5, without thinking about it. Oh well, that's the end of this section. Thank you everybody for watching. Bye.